given this distribution of loads and the moment and shear that we determined before, we now have the experimental values of the strain at this point. This is strain 1. This point, this is the second experimental strain. Strain gauges 3 and 4 are located right there. Strain gauge 5 here, 6 here, and then strain gauges 7 and 8 are located right there. We've, based on our shear and bending moment diagrams, determined that the moment is going to be constant from this point to this point. So we know what the moment is going to be at the points of these. For strain gauges 1 and 2, the moment, we don't know exactly what that is because that varies between this point, and we haven't measured exactly where along this direction those are. However, those are located at the neutral axis, so we don't need to worry about moment stresses for that. We only need to worry about shear stresses, and the shear is constant from this point to this point. So we're fine on that. When we're trying to determine what our theoretical strains are, we're going to use a couple of equations that by now should be very familiar to you. We're going to want to use our normal stress equation for bending moment. That's going to be that the normal stress is going to be equal to the moment, which we said was constant from here to here, times the distance from the neutral axis to the point that we're considering, divided by the second moment of inertia. And we're also going to use the equation for strain. Let's draw a nice line to differentiate between the equations. The strain, we're going to have the strain in the x direction. We've got basic Hooke's law, right? Which is to say, it is the stress in the x direction divided by the Young's modulus minus Poisson's ratio times the stress in the orthogonal directions divided by Young's modulus. But we already know that there is no normal stress in the y direction. That will go to 0, as will this. So we can get away with using the simplified uniaxial definition for Hooke's law. Shear strain will be a little bit more involved, only slightly though. We'll want to use this equation, where the shear stress is equal to the shear force times the first moment of area divided by the second moment of inertia and the thickness of the web. And we'll want to use the definition of shear strain, which is that it's the shear stress divided by the shear modulus. Now, we've already determined what the moment is and the shear is across the length based on our shear and bending moment diagrams. The Young's modulus and the shear modulus are given to you, as is the thickness of the web. So, you will need to be able to calculate the second moment of inertia and the first moment of area.